Hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. Well, let me take a break here before everything begins. Why quantum mathematics? And I think you should just check my title again, like the title of my YouTube channels, like name. Earlier it was Quantoffy, and from that earlier, from that previously, it was quantum mathematics itself. But why did I again? I'm sorry. Again, I changed it to quantum mathematics. Actually, Quantoffy was like it was quite kind of weird, right? And it didn't have some kind of meaning, so that's why I just changed it to quantum mathematics. Actually, it looks quite convenient, I think, rather than that Quantoffy. So that is why I changed that. And again, maybe this is again a new journey here with quantum mathematics, and we're just going to begin our journey with Gaussian, Carl Friedrich Gauss, the prince of mathematicians or mathematics. Actually, we are just going to take a look at the Gaussian representation of the gamma function. So this is the representation of that Gauss has invented or calculated or formulated himself. So basically it is saying that gamma of z equals limit n tends to infinity of n to the z over z times the product as k goes from 1 to n of k over z plus k. So that is simple. And you know what? Okay, till now you might have taken a look at this board, and it is like it is like congested. Every word just wanted to get independent of this board or get wisdom from this board, because everything is like just pushed into each other actually. But it's all right. That is the Weierstrass infinite product of the gamma function. So basically, I was just writing the whole formula for that, the derivation. So I just got that, if you can see there. So to prove this down, like the Weierstrass infinite product for gamma function, if we want to prove that down, we need to use of this very equation. So basically I was looking to prove this in front of you all, but then I got to have, let's prove this down firstly. And we can do this, we can prove this down on the basis of our knowledges that we are here till like after just looking at all my old videos. So basically we are just going to begin with the basic gamma integral, that is integral from 0 to infinity of e to the z minus 1 e to the negative t dt. And you guys, if again, I'm highly recommending you guys to just watch the video of the introductory part of this gamma function, because in that video I have formulated this integral as z minus 1 factorial, and which is gamma of z. So that is why I'm requesting you to just please watch that video. And that is why actually the Weierstrass product cannot be, or I'm not sure, but this is easy. So we have to learn about this one, or I'm not sure that Weierstrass product can directly be proven by this one. But yeah, if I got something like that, so again I'll bring it for you guys, don't worry about that. So I think we should just continue with the proof of this crazy equation or the crazy formula for gamma function. Okay, so basically again as I just told you that we just have to begin our journey with this gamma like integral representation, right? So let's just dive into it, guys. So okay, so basically our journey begins from here. We know that it's integral from 0 to infinity of e to the z minus 1 e to the negative t dt. Okay, so yeah, it's good. Now I'm assuming that, let's consider z sub n, integral from 0 to n t to the z minus 1 e to the negative t dt. So what I have changed here, like how can I reach here from here? Like how can I reach gamma of z from this z sub n? So when you plug n equals infinity, or maybe n tends to infinity, so you can just reach up to there. So basically the relation between this z sub n is limit n tends to infinity of z sub n is gamma of z, because then n would be replaced with infinity and hence you are having gamma of z. That is why, right? So yeah, this is quite convenient here, and we are just going to continue here from here itself. And again, one thing you need to know about here, that is e to the negative t is often represented as limit n tends to infinity of 1 minus t over n to the n. So it's another a very classic representation of e to the negative t. Or if we talk about e to the t, so you just have to replace, or you just have to change this negative with positive sign. So yeah, that's fine. So again, we're just going to replace this with here actually. And since we are assuming that n is tending to infinity, so we will not consider this limit, because eventually when we take finally the limit n tends to infinity to represent this gamma of z, so that will just include all the n terms actually. So rather than just writing this term, we can just continue without this. So basically we are having z sub n equals integral from 0 to n t to the z minus 1, yeah, and then this 1 minus t over n to the n dt. Okay, and now comes the crucial part, and in this part, like I'm going to evaluate this integral, and for the evaluation of integral you just have to be focused very much, because we're just going to use di method, and that too n times. So we just have to take care about every step carefully. So basically I'm just going to do that right here, and I would take this whole board, or maybe we would be need to erase this also later on. Well, let's see that. So I hope you are familiar about DI method, and yeah, I have used it multiple times in my old videos, so you can just check that out. But if you want, yeah, it's and maybe I would say a easier part of by parts. That's it. Easier way of doing by parts. That's it. So we have two functions in our integrand actually. The first function is this one, and the second function is this one. So basically we're just going to take the derivative of this function and the integration of this very function, right? So let's talk about this one. 1 minus t over n to the n, and integral t to the z minus 1. Okay, now for this function we have to just take care about the power rule as well as the chain rule, right? Because we have this function as well as this function, so we just have to care about that two things simultaneously. So if we differentiate it with respect to t, so that's going to give us n times 1 minus t over n to the n minus 1, and with the chain rule we can say it's 1 over n, because the derivative of 1 is 0, and the derivative of this very function, like the negative t over n, is with respect to t is negative 1 over n. So I hope you can understand that. That's quite easy to understand. And it's t to the z over z. Okay, next again do that. So it's plus, and that is n times n minus 1, right? And it's 1 minus t over n to the n minus 2. And let's consider, well, yeah, let's consider this negative 1 over n to here, and again with the chain rule we can say it's negative 1 over n. And since, look, this negative and this negative, like being multiplied to each other, they both are going to give us positive sign, right? And next would be negative. So I hope you understand that. I just said you, and I warned you that this is the crucial part, and you just have to understand it. If you want to just prove this down, you need to understand this part very carefully. And then the integral of a to the z over z is e to the z plus 1 over z times z plus 1. Okay, and finally last time here, so it's n times n minus 1, again just taking this in front, so and n minus 2 as well, so that is n times n, and it's 1 minus t over n to the n minus 3, and it's negative 1 over n due to chain rule, right? And if you take the integral of this one, so it's t to the z plus 2, z times z plus 1 times z plus 2. So let me just check that whether you guys are you can just see all the stuffs or not. I think you can just see that. Yeah, that's fine. And this keeps going up to n times, right? So basically, we would be saying that, let's consider that, let me tell you something here. Basically, when these two things are being multiplied to each other, like this negative and this negative, they're going to give us positive, and this negative times this negative, positive, this positive, positive, positive. Eventually, our very last part, it's gonna be integral, right? So it is gonna be a positive. So I will consider that our last term is positive 1 over n. So plus, I will consider this as, like, it doesn't mean at all. And yeah, actually, you know what the crazy part here, all these things are gonna vanish. Like this, I'll tell you, it's a magic. It's not a magic, but maybe it's a mathematical slightly magic by none other than Gauss. Okay, so let's come back to our point here, and we are, so it's n times n minus 1, n minus 2 dot 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 3 to 1, right? And look, n times n, it's 3, so it's n cube. It means if we are going to vanish this term, so we would be having n to the n here, right? Because n is n times, so it's n to the n. So yeah, that's it. And okay, wait a second, and yeah, it's fine, it's perfectly fine. And here we would be having t to the z plus n minus 1 over z plus 1, z plus 2 dot 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 to z plus n minus 1. That's it. Yeah, it's perfectly fine. But like till now, it's perfectly fine. And now crisscross methods actually, and this is inside an integral. Actually, why we did that, to get rid of this 1 minus t over n to the some power. Okay, now let's just let me just show you the magic here. So here we are going to just look at the magic. The magic is really amazing, guys. Okay, so now let's play around a little bit with that. So it's our z sub n is t to the z over z, 1 minus t over n to the n. Fine. Then this one. So it's negative times negative is positive. Basically, this times this one is a positive term. So basically, it is saying that it's n 1 minus t over, let's plug that here in front, 1 minus t over n to the n minus 1, and times t to the z plus 1 over z plus 1. Okay, next, plus this term times this one. So that is gonna give us n times n minus 1. Wait a second. Yeah, it's fine. N times n minus 1 over n times n actually, right? And then we are having 1 minus t over n to the n minus 2, and then t to the z plus 2. Oh, I think I just missed a z here. Oh yeah, t to the z plus 2 and z times z plus 1 times z plus 2. And if this is keeps going, dot dot dot, evaluating this from 0 to n, don't forget about the limits, bounds actually, and this is inside an integral part. So basically this is n factorial, right? N times n minus 1 times n minus 2 and dot 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 to 3 times 2 times 1. It's n factorial. So we can just represent that with that. So it's n factorial over n to the n and times this whole big factor, that is z plus 1, z plus 2 dot 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 z plus n minus 1 integral from 0 to n z, t to the z plus n minus 1 dt. Okay, it's perfectly fine. Now, what's the magic here is, let's talk about this part only. Let's not consider the integral part because that's a different thing for now, but we will consider it later on. But for now, let's consider this part. So firstly, plug n in all the terms respectively. So when you plug n here, so on the place of t, be careful. So it's n to the z over z, yeah, it's fine. And 1 minus n over n, which is n over n is 1. So 1 minus 1 is 0. So basically this term is 0, right? Yeah, it's fine. And so for the next term, because in each and every term we are having a factor of 1 minus t over n, and when we replace t with n, so we're gonna have a 0. So basically when we replace t with n here, so we are just going to have 0 in each term. So yeah, n is out. Let's talk about 0. So 0, when we replace 0 here, it's 0. 0 here, 0. Like in each term, another factor is t to some power. And t is being replaced with this 0, and that's fine. It's completely 0. It means it is also out. So basically this whole part converges to 0. And this is the magic, like this was the magic. Gauss. So finally we are left with z sub n factorial over n to the n z plus 1 z plus 2 dot 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 z plus n minus 1. And when we integrate this, so we're gonna have a factor of z plus n in the denominator, and it's just a power rule of integration. So it's it's n to the z plus n, and basically this can be written as n to the z times n to the n, right? Yeah, you can evaluate this integral, so you're gonna have this very part here when you evaluate that. So again, a cancellation here, n to the n getting cancelled with that. Oh, I'm sorry, I'm really sorry guys. And again, I just missed a z here. Yeah, I have written over there. So that was the magic. So n to the n is being cancelled out with this n to the n, and we are left with n factorial times n to the z over z times z plus 1 times z plus 2 times dot 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 to z plus n. Okay, now we are very close to our final result. Oh my god, my chalk has broken. Okay, so basically we are adding here, wait a second guys, let me just use the stock. So our z sub n here is n factorial over z times z plus 1 times z plus 2 dot 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 z plus n, and it's n to the z. Let's consider just plugging out n to the z over z as a factor of this, and it's n to the z over z, and it's, if we talk about this part here, So this can be represented as a product, that is a product up to n as k goes from 1 to n of k over z plus k. And if you evaluate this, like when you plug k equals 1, so you're gonna have the last term of n factorial. And if you are just multiplying this up to n times, so basically you're gonna have its n factorial and it's z plus 1 times z plus 2 times z plus 3 and dot 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 to z plus n times. So basically here is your result that we are looking for, but still it's quite not convenient here, not supportable actually, because we considered limit n tends to infinity of z sub n was gamma of z. So let's just multiply, let's just consider taking limit n tends to infinity both sides. So here if we consider limit n tends to infinity of z sub n, that was our gamma of z, and limit n tends to infinity of n to the z over z times the product as k goes from 1 to n of k over z plus k. And hence I'm just going to write down the final result after replacing that limit n tends to infinity of z sub n as the gamma of z. So here is your Gauss representation of gamma function. Gamma of z, this whole part is gamma of z, equals limit n tends to infinity of n to the z over z times the product as k goes from 1 to n of k over z plus k. Hence proved, guys. So that was the gamma representation. Gamma representation as a limit that tends to infinity and some products by the Carl field Gauss. So it was really great actually, guys, and we got to learn a lot of things, guys. Actually, now I can legally talk about the Weierstrass infinite product for gamma function, because we have proved this equation. So we're just going to use this one to prove this down, but I'm just going to take another video for that. Although I can do this in this video only, but I think we should just keep it separate. Okay. And again, guys, if you got to learn something from my video, so please make sure to just like and subscribe. And if you have any kind of doubt till now watching this video, if you got any kind of doubt, you can freely ask in the comments, and I will make sure to just reply to that question. So yeah, I think it's fine, and just wait for the next video in which we're just going to prove this Weierstrass infinite product for gamma function. Or I think I should just write that down if you cannot see that. So let me just consider writing that down for you, because maybe that's gonna increase some curiosity in you guys for just coming for the next video, that quantum mathematics is just calling us for his next video. So the Weierstrass, it's Weierstrass infinite product for gamma function is, it's the reciprocal of the gamma function equals e to the Euler masculine times z. Actually there's a factor of z in front as well, and the product as k goes from 1 to infinity of, I think it's it's 1 plus z over k times e to the z over k. I'm sorry, it's negative. Yeah, it's a negative factor. So yeah, that is the Weierstrass infinite product for gamma function, and we would be proving this using this one only. Yeah. So yeah, that is really amazing, and I just did that here, but I would highly recommend, or I would highly request you to just come up with my next video to just have a great journey, to have a great feeling of this journey, this world actually. So yeah, thank you so much for watching this video, guys. If you got to learn something, oh, I already asked you that. I already asked you that, so I don't mean to ask that again. It's crazy. Okay, so now I would just take a leave and just come back in the next video. We would be learning a lot of things. Just hashtag Gaussian Gaussian representation and the Weierstrass infinite product. Goodbye, guys. Take care.